Welcome all. Today we are going to do the numericals of chapter heat transfer based on thermal conductivity. The first numerical that we are considering is unsolved question 2 of your textbook. The area of cross section and the thickness of an iron plate are given as 2 centimeters and 5000 centimeters square. As you can see in the solution, they have been converted into their SI units. The temperature of the surfaces theta1 is 150 degrees Celsius and theta2 is 140 degrees Celsius. So we have to calculate the rate of heat transmission. The coefficient of thermal conductivity for iron is 0.015 kilocalories per second per meter per degree Celsius. So using the formula Q upon T is equal to Ka theta1 minus theta2 divided by L, and on substituting the various values of the quantities mentioned, the rate of transmission of heat is 375 into 10 to the power minus 2 or 3.75 kilocalories per second. If you want, you can also convert your answer in terms of joules per second, which can be written as watt also. Next is question number 5. There are two rods A and B. They have the same metal. They are of the same metal. That means their thermal conductivities are going to be same. The area of cross section is also given as same, and they are both immersed in ice at 0 degrees Celsius. So one of the temperatures is theta1 given to you as 0 degrees Celsius. In which rod will the rate of transmission or conduction be more when, in the first part, the rate their other ends are at the temperature 20 degrees and 30 degrees Celsius respectively, and length of A is half the length of B. The areas of cross section are also given as equal. So the rate of transmission of heat, if you see, will now depend upon the difference in the temperatures divided by L. So the difference in temperature for A is 20 degrees Celsius, while for B it is 30 degrees Celsius. I've used P as the symbol for rate of transmission of heat. So PA upon PB comes out as 4:3. Therefore, the rate of transmission for A is greater than the rate of transmission for B. In the second part, the end of rod A is at temperature 20 and B as 10 degrees Celsius. Also, the length of A is twice the length of rod B. So moving exactly in the same way as we did above, the rate of transmission of heat will depend on the ratio of the change in temperatures divided by their lengths. So the rate of transmission for A upon B comes out as 1. Therefore, they have the same rate of transmission. Let us now take question number 7. The opposite faces of an iron cube are in steam at 100 degrees Celsius and in ice 0 degrees Celsius. So theta1 we'll take as 100 and theta2 is 0 degrees Celsius. The length of the cube is given as 2 centimeters. So its area of cross section of the cube will be 4 centimeters square. The thermal conductivity of iron is 0.2 calories per second per centimeter per degree Celsius. We have to calculate how much of the ice will melt in 5 seconds. The latent heat of ice is 80 calories per grams. So we are going to calculate first the amount of heat that is flowing or getting conducted, which is Ka theta1 minus theta2 into T divided by L. So K is 0.2. The area of cross section is 2 into 2. The difference in the temperature is 100 minus 0, that's 100, and the time is 5 minutes, which has been converted into seconds divided by the length, which is 2 centimeters. So the amount of heat conducted or transmitted is 12 into 10 to the power 3. So Q is equal to ml, and therefore the amount of ice that melts is Q upon L. That comes out as 150 grams. Question number 10. Two rods of same metal and same area of cross sections have lengths 0.5 and 0.8 centimeters. The temperature difference across the ends of the first rod is given as 40 degrees Celsius, and we have to calculate the temperature difference for the second rod if the rate of conduction is equal in both the rods. That means Q upon T for A will be equal to Q upon T for B. They are of the same metal, that means their thermal conductivities are same, their area of cross sections are same. Therefore, the difference in temperature of A divided by its length will be equal to delta T, which is the difference in temperature for B divided by the length of B, that is 0.8, and the difference in temperature across the ends of rod B comes out as 64 degrees Celsius. Next question that we are considering today is question number 15. Two plane surfaces of two sheets of different metals are kept in contact with each other. As you can see in the diagram, A and B are the two sheets. The thickness of rod A is being taken as 2.5 centimeter and for B as 3 centimeters. The ratio of their conductivities is 5:6 respectively. If the outer surfaces are at constant temperatures of 100 degrees Celsius and 10 degrees Celsius, then we have to calculate the temperature of the interface. So theta 1 is 100 degrees Celsius, theta 2 is 10 degrees Celsius. We have to find the temperature theta of the interface. Now, as the rate of flow of heat in the whole system will be same at steady state, therefore Q upon T for A will be equal to Q upon T for B. So substituting the values of Ka, theta 1 minus theta 2 and L for A and B, we get the relation 5K into A, 100 minus theta upon 0.5 is 6K A into theta minus 10 divided by 3. Solving the two equations, we get the temperature of the interface as 55 degrees Celsius. Heat will flow from theta 1 to theta 2, so you have to consider theta will be lesser than theta 1 but greater than theta 2, which we are getting as 55 degrees Celsius.